Principle of moments, rotational equilibrium. Thanks for watching this video and don't forget to like, subscribe to the channel and activate the notifications. It is very important to the continuity of this channel. When a force is applied to an object that is not a point mass, it may rotate, and we know the turning effect of a force is called its moment or torque. Look at the figure. If a force is applied to an object, it can rotate around the fixed point about which it will turn in one of two directions, clockwise or anti-clockwise. By convention, when an applied force causes an object to rotate anti-clockwise, the torque on the object is positive. When the force causes the object to rotate clockwise, the torque on the object is negative. A torque that rotates an object anti-clockwise is a positive torque. A torque that rotates an object clockwise is a negative torque. If a body is acted on by more than one force and it is in rotational equilibrium, by rotational equilibrium I mean that the body is not rotating, so the resultant torque about any fixed point must be zero. This is sometimes known as lever principle or principle of moments. The principle of moments states that for a body to be in rotational equilibrium, balanced, the sum of clockwise torques about any point, which acts as a pivot, must equal to the sum of anti-clockwise torques about the same point. A woman of mass 55 kilograms sits on the left end of a seesaw, a plank of length 4 meters, pivoted in the middle. A man of mass 75 kilograms sits on the right 1.2 meters from the pivot. Is the seesaw in equilibrium, balanced, or will it start to rotate? To see if the seesaw is in equilibrium, we need to think about each force individually. Which direction each force is trying to turn the seesaw, clockwise or anti-clockwise. We calculate all the moments about the pivot. The weight of the woman on the left tends to turn the seesaw anti-clockwise. The weight of the man on the right tends to turn the seesaw clockwise. You should note that the torque of the weight of the plank is zero, since its distance from the pivot is zero. Anti-clockwise is greater than clockwise. Therefore, the seesaw is not in equilibrium, and it will start to rotate anti-clockwise. A box is balanced on a uniform plank of length 2 meters with a pivot 50 centimeters from one end, using a 20 kilograms mass placed at the end closest to the pivot. If the center of gravity of the box is 40 centimeters from the other end of the plank and the mass of the plank is 5 kilograms, calculate the weight W of the box. In rotational equilibrium problems, we always start our answer by stating sum of the clockwise moments is equal to sum of the anti-clockwise moments. We now take the torques about the pivot. One force acts anti-clockwise, the weight of 20 kilograms mass at 0.5 meters. Two forces act clockwise, the weight of plank at a distance of 0.5 meters and the weight W at a distance of 1.1 meters. We now perform the calculations. The weight of the box is 66.8 newtons. The diagram shows a design for a crane. The crane is controlled by a computer. The purpose of the motors and gears is to change the pulling force in the steel cable. This is done so that the jib stays horizontal whatever the size of the load or the position of the load. Use the equation in the box to answer questions A and B. Calculate the moment caused by the load in the position shown in the diagram. Show clearly how you work out your answer and give the unit. The moment or torque caused by the load is its weight times 6.4 meters. Calculate the pulling force that is needed in the steel cable to keep the jib horizontal. Show clearly how you work out your answer. We now apply the principle of moments to calculate the pulling force that is needed in the steel cable to keep the jib horizontal. The pulling force is 16,000 newtons.